This video will deal with the topic of bond polarity. By the end of the video, the objective is that you can determine the bond polarity for the individual molecules. And from that, also determine what type of bond it is and also create dipole moment arrows. So it's kind of threefold. So what's the deal with bond polarity? Well, it has to do with covalent compounds. And as we know, for covalent compounds, two different atoms are sharing electrons between the two of them to complete their octet. But the deal is, when we talk about the word share, share does not imply equal. Share means that each party gets to have an object at some point, but they do not get it to equal amounts of the time. You can see this picture here with one boy having the truck more than the other. And you know it's the case in life. When you're sharing, you don't always share equally. This happens in covalent molecules also. When two elements come together to share electrons, they do not share them equally in every case. And because of that, we actually have two different types of covalent bonds. So, the two different types of covalent bonds are non-polar covalent bonds. In those cases, you have two elements coming together. Neither one is able to pull electrons more than the other, and so they share their electrons equally. The electrons that are being shared are evenly distributed between the two elements. We also have polar covalent bonds, and in polar covalent bonds, what's happening is the two elements are coming together, but one element is able to pull the electrons more strongly than the other element, and because of that, the electrons are not evenly distributed between the two elements. They're uneven, and that makes it a polar covalent bond. Polar, you know, things like the North Pole and the South Pole. Poles are usually locations, and in this case, with polar covalent bonds, what we create in a polar covalent bonds are locations with charge. Okay? So a polar covalent bond is a bond that creates poles of charge on the atoms. Here's a picture of what this can look like. The top model here, model A, is actually of a non-polar covalent bond. The two black dots are the nuclei, and the blue shape around it is the electron orbital, okay, where the electrons reside. And you can see here is a very symmetrical orbital overlapping both nuclei evenly, and the electrons reside within that space, meaning neither one is pulling more than the other. The electrons are evenly distributed. B instead shows a polar covalent bond. You can see here that the orbital is no longer symmetrical. One side of the bond has a larger region where electrons reside than the other. There's a bigger blue circle on one side than the other. Okay? And that's because there's an uneven share. One side of the bond is basically has the electrons more often than the other side. And what you can see on top of this shape are what we call partial charges. Okay, that symbol looks like this. It's either a minus or a plus. These are actually lowercase deltas. They mean partial charge. Okay, so when you have a symbol like this, practice drawing it. It's a lowercase delta. It's like a D with a tail on the top. That means partial charge. It means there's an unequal distribution of electrons, but there's not a full separation with an entire electron charge. There's just an uneven distribution. The C model, on the other hand, is the ionic bond then, where you have a full separation of charge. There's actually a separation of the orbital, which makes one nuclei contain a negative charge and one contain a positive charge. Okay. So top one's nonpolar, middle one's polar covalent, and the bottom one is ionic. This is your distribution or your types of bonds that you can encounter. One thing I want you to realize is this is kind of a spectrum. We start to look at this as a spectrum in that it's all about how well the electrons are being pulled. If there's no pull, it's nonpolar. If there's some pull, to even a pretty great amount of pull, you can have polar covalent. Until the moment where you have enough pull that basically the electron no longer resides in the orbital around one of the atoms, that's what creates ionic. So it's kind of a spectrum, and then it just depends on how firm the pull is. How do we know which bond we're going to end up with? What we use for this is your electronegativity chart. Okay, this shouldn't be a surprise. Electronegativity is the tendency to attract electrons to yourself. So if we're talking about situations where either you're going to pull electrons more or less, that's going to be measured by your electronegativity. Okay? How do we measure it? Well, what we do is we look at the difference in the electronegativity between the two atoms doing the bond. If the difference is very small or none, you don't have a difference in pull, in which case you have a nonpolar. If you have some pull, and even a decent amount of pull, you'll end up with polar covalent because you'll have an unequal distribution. And then at some point, the difference gets so great that one is actually able to rip the electron away from the other. You have an electronegativity chart on the back of the periodic table I already gave you. And this is what you're going to use as we try to determine if our bonds are nonpolar, polar, or ionic. So what are the numbers that tell us? If we calculate the difference in electronegativity for our two elements in a bond and we get 0.3 or less, that is nonpolar covalent. If we get between 0.3 and 2.0, so from 0.4 up to 1.9, that's a polar covalent bond. And if we get 2.0 or higher, that's ionic. So those are our breaking points. And what you'll find here is it's not always that if there's a metal, it's ionic. It has to do with the difference in electronegativity. So if you don't have a very weak electronegative metal or a very strong nonmetal, sometimes we don't have full separation. Okay? So that rule kind of goes away once we get to electronegativity. Again, it's a spectrum, meaning as you get more difference in electronegativity, essentially the amount of covalent sharing decreases and the amount of ionic increases. So let's try some of these. Here's a huge list of ones to try if you want to. I can post answers to this, but I'm just going to do these 4 back here for you so you can see how you use electronegativity difference to determine the type of bond. So we start at the top with this cesium and bromine. If you look for cesium on this chart, right here I have an electronegativity value of 0.8. And for bromine over here I have a different of 3.0. The electronegativity difference is just the difference between the two. Always make it positive because it's just the difference. So if I subtract one from the other, is this right? 3.0. Yeah. If I subtract one from the other, I get 2.2. Hey, look, that's above the 2.0. That's ionic. And it shouldn't be shocking to you since cesium is a metal. So this is actually an ionic bond. Okay? And we sometimes label this as our change in En, electronegativity. Let's do NO. N is 3.0. O is 3.4. The difference then between them, the difference or the change in electronegativity is 0.4. That's above 0.3, right? So this one would be polar, covalent. LIN, you can already predict what you think it will be because we have a metal, but we can just verify 1.0 and 3.0. Subtract them, you get that change in electronegativity to be 2.0, which means it's ionic. You're right. And this is a pretty classic nonpolar. Hope you can already kind of see why it would be, in that when we have two of the same exact elements bonded, their electronegativity difference is going to be 0, which makes them non-polar. Okay, pretty straightforward for that one. So if we're trying to determine which type of bond you have, you look at their electronegativity difference based on what the chart has, and memorize the numbers, the 0.3 and 2.0, and you got your bonds. The other thing I want you to be able to do is draw something called a dipole moment arrow. Here's the deal. Whichever one has a bigger electronegativity, that's where the electrons are more often, right? That's where the larger orbital is. When that happens, you create a partial negative charge on that particular element, which means you create a partial positive charge on the other element. What a dipole moment arrow is it shows us how these charges are actually working within the atom. So it's an arrow that indicates the direction of pull, and this arrow is a vector. And if you know what a vector is an arrow that shows you the direction of a measurement and the magnitude. With the direction and the magnitude, eventually we're going to apply that to figuring out the polarity of an entire molecule. But for now, I just want you to be able to create them. So number one, this only happens if it's polar, because for ionic, say like for this one, which is ionic, this nitrogen is actually taking the electrons, right? It's going to end up being negative, and lithium is going to be positive. Those are full separations of charges. And down here for bromine, there's no unequal share. It's going to be totally neutral. But right here for the nitrogen and oxygen example, oxygen has 3.4 and nitrogen has 3.0. So oxygen is going to be, it is more electronegative, which means it's going to have the electrons around it more often. And we denote that by creating these partial charges. Okay? It's going to be negative because it has electrons more often. And the nitrogen is going to be positive. Okay? And then how you create a dipole moment arrow is you put basically a positive sign on the positive atom, and then you generate an arrow that's pointing toward the negative atom. So you're pulling your electrons in this direction for that particular bond. Okay? So there's other example on this screen with hydrogen and fluorine. Hydrogen has a measurement of 2.2, fluorine is 4.0. So the difference between these two is 1.8, which gets you polar covalent, right? The change in electronegativity is 1.8. Fluorine is your more electronegative, so that one is going to be the negative. Hydrogen is the positive. So to create your dipole moment arrows, you put the plus on the hydrogen side and you draw your arrow towards your fluorine. So if you need to, there's all of these practice, and I'll put the answers up. You can determine which types of bonds these are, put in dipole moment arrows, put in partial charges and all that to make sure you can do the objective. Because again, the objective is that after this video, you can determine the type of bond by doing the electronegativity difference. You can assign charges, and you can create dipole moment arrows. I'll see you guys tomorrow.